Okay. Sorry, I just scrolled down. Oh, let me get rid of that. So I realized there was something that I haven't talked about in my videos that is going to be important moving forward, and it is on the pretest, and I forgot about it. So just in case you have a chance to review it beforehand, which isn't necessary, but I want you to be able to prepare yourself and have references. Let's talk about evaluating piecewise functions from graphs and algebraically. And I'm going to break this into sort of 2 to 3 sections. 2 sections are going to be very helpful for you. The first 2 sections when we're doing graphs here, and when we're doing it algebraically, that's going to be, both of these are very helpful. The third section is going to be more of like a deeper understanding to try and help you get some concepts a little deeper. Okay, but let's look at this. Evaluating a graph, still pretty straightforward. We have our input of -2. We're looking for where is our input, -2, what is our y value, what is our output value at -2, and in this case it's 4. Our output is 4. Okay, our output is 4. What makes piecewise functions tricky is there are going to be open dots in them, unless it's a lot of the ones we'll work with will have open dots because they're not as interesting if they don't have open dots. But now we'll look at our input of -1. Oh, by the way, open dots are dots that have nothing filled in. I have a picture of an open dot right there. Open dots are right here. And if you wanted to, as an exercise, you could identify all the other open dots. But f of -1, if we come here, we have a gap in our function. It goes from 1 to 0.5. And what do we do with that? Well, these open dots mean that our function is not defined at this point, which that I'll give you, that's going to be my section 3, is talking about what does it mean when a function's not defined, or how can you wrap your head around that. Okay, but for now, all I'm going to say is we need to look for closed dots. So at f of -1, our function is not defined here, but it is defined here at 1. So our output is 1. And now we'll go to f of 1. We have our input of 1, and we have another gap in our function, which there's a technical name for that, but we're going to talk about that in class, so I'm not calling it that yet. This gap in our function has 2 undefined points around it. There are no closed dots. So what I said before, at an open dot, our function is not defined. So here at f of 1, our function is not defined. Our function is, I'm actually not even going to use, I'm going to use a different, I'm going to use this one. Our function is undefined. At this point, we have no closed dots there, it's undefined. Okay, and now f of 2, this is our input. F of 2, another interesting situation happens here. We have an open dot, a gap, we have an open dot, a gap, a closed dot, another gap, and an open dot right here. And again, at these open dots, our function is not defined, our function is undefined, but we have a closed dot here that tells us our function is defined at this point. So when our input is 2, our output is 5. And that's evaluating from a graph. So now moving to algebraically, this is going to come up again. This part is not on the pretest, so if you wanted to wait on this until later, it would make sense. But this will be very helpful towards the end of our first unit, before we get to expanding expressions, but Yeah, before we get to expanding expressions, this will be helpful, but it's still near the end. So we have h of negative 1. And if we're evaluating this piecewise function, we need to look for where is our function defined? Where is our function have an input value of negative 1, in this case t. When does it have a t value of negative 1? Well, it has a t value of negative 1 here, because this is less than or equal to. So t can be equal to negative 1. That means it has a value there. So I'm going to take my first, my linear part of this, 2x plus 1, and I'm going to take my input, negative 1, and I'm going to put it in to my function, and that gives us negative 1. h of 3, I'll leave you to do as an exercise, because I think I've given you enough information. H of 5 is tricky. I want you to pause and think about what would h of 5 be? Okay. And for h of 5, what I expect some of you might have done is you might have looked and said, well, I have a 5 here, and I have a 5 here for my input value. I also have a 5 here. But this is an expression. Well, this is an expression. This doesn't have any variables. There's nothing for me to do here. So you might have tried, and this is wrong, to go 4, 5, minus 2. That would be wrong. That is not where your function is defined at 4, 5. And if you might have done a similar thing with x squared. So I'm going to get rid of that. This one is actually really simple. It tells us that when our input is 5, when t equals 5, our output, that's what this column is for really, our output is 4. So for h of 5, our output is just 4. That's it. Okay. And now h of 6, we don't have anything in our inequalities to tell us where h is 6. So we just need to think which one would it fall into. I really should have also done, actually I'll leave that as for an exercise for y'all as well. Find h of 2 and find h of 4. See if you can evaluate those using what I'm telling you for h of 6. So for h of 6, which one would it fall under? Well, t is greater than 5 here. 6 is greater than 5, so my input of 6 makes sense for this one. So all I'm going to do is put it in, because it's my input. So I'm going to do 6 squared. 6 squared is 36. Okay. And those are the two big sections I want to talk about. This third section is really going to try and illustrate what's happening when we get to sort of an undefined point. This is something that my sort of college professor talked to me about, not even in my calculus class, but in a far later class. But let's say, and we're actually going to do a two-dimensional number line. Let's call this 0 and let's call this 1. And let's say, oh my god, y'all can't see my screen. Okay, third section. I drew a number line, it goes from 0 to 1. Let's say this is 1 mile. Let's say it's 1 mile, 0 miles. A person runs half a mile. And then they run half of that. They run a quarter mile. And then they run an eighth of a mile. And they keep going by halves. They keep going halves and half. So we have 1/16 there, 1/32, 1/64, 1/128. We keep going, we keep going, we keep going. And the question is, do we ever reach 1 mile? If we keep going halves and halves and halves and halves and halves, are we ever going to really be at 1 mile? And this can actually sort of be represented by an equation as well. So if we do 1/2 to the n, f of n equals 1/2 to the n. If you were to put that into a calculator, if you were to put that into Desmos or somewhere, you would see that the graph of this, let me zoom out a little bit for myself. The graph of this, it's not a continuous graph, but you start at 0, looks like that. And if you remember from Algebra 2, maybe pre-cal, that this is actually an asymptote. And connecting that back to what we were doing with graphs, because that was my whole point for this, is that is more or less what is happening at these open dots. Is that we are touching every single value going to it. It's well, doing only these halves isn't going to get us to every single value, but the idea is still the same. We're getting closer and closer and closer and closer to this, but we are never going to touch it. It doesn't get there. And so we use this open dot to show that it's touching every value before this. It's touching, let's see, this is -1. It's touching negative 0.9999999999999999999999999 forever. 0 point as close as you can possibly get to -1, but it doesn't touch it. And for me, seeing this kind of visual demonstration down here, that's kind of what made it hidden for me, because the answer to this question, do we ever reach 1 mile? Well, the answer is no. We never actually do reach 1 mile, because we're getting very, very as close as we possibly can to it. But the thing is, we can always keep getting closer. There's no stop to it. So hopefully that gives you a little bit more of understanding as what's happening with an open dot is it's almost in a way the function having a kind of asymptote. It's a value that it never reaches. Asymptote's not the proper word to use, so I wouldn't use that in a formal explanation, but that's sort of what's happening at an open dot, is we're getting infinitely close, but never touching. Okay, hopefully this is helpful. There are going to be questions like this section up here on the pretest tomorrow. All right, good luck.